Somewhere in the quiet dark of our galaxy, a world is turning. It has no continents, it has no shorelines, it has no mountains rising into a thin blue sky. From far away, it looks like a soft blue marble, larger than Earth, but smaller than Neptune, wrapped in a haze so thick that no telescope on our planet can quite see down into it. Beneath that haze, if the theories are right, lies an ocean, not a sea between lands, not a basin filled with salt water, a single endless ocean covering the entire world. This is the kind of place astronomers have begun to imagine, and it is the kind of place we will spend the next few hours wondering about together. The name some researchers have given to these worlds is Hycean, a soft blend of the words hydrogen and ocean. The idea is simple to picture and very hard to confirm. Imagine a planet 2 or 3 times the size of Earth. Now wrap it in a deep, puffy atmosphere of hydrogen and helium, the 2 lightest gases in the universe. Beneath that warm blanket of gas, water stays liquid across enormous depths. The whole surface, if you can even call it a surface, is sea. We do not yet know if these worlds are real in the way we hope. We have candidates. We have hints in Starlight. We have careful arguments and careful counter-arguments. What we do not have is a clear photograph or a probe or a sample. The mystery sits with us, patient and quiet, waiting for better instruments and better minds. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. So picture the view from far above. The star this world circles is small and cool, a red dwarf perhaps, glowing the color of a dying ember. Its light falls gently on the planet's hydrogen sky, scattering through layer after layer of haze. From a distance, the planet glows a deep, muted blue, the kind of blue you might see in old glass held up to a candle. There are no city lights. There are no clouds shaped like the ones we know. There are bands of pale vapor, slow and wide, drifting across the upper air. Worlds like this sit in a strange middle place in our growing catalogue of exoplanets. The planets that orbit stars beyond our sun. They are bigger than Earth, smaller than Neptune, and our own solar system has nothing quite like them. We have rocky little worlds close to the sun. We have gas giants further out. But between the size of Earth and the size of Neptune, there is a whole class of planet we are only just learning to read. Some of them are dry and dense. Some of them are puffed up with gas. And some perhaps are these warm ocean worlds, hidden under hydrogen skies. The numbers are staggering even if we hold them loosely. Statistical surveys suggest that planets in this size range are among the most common in the galaxy. If even a small fraction of them turn out to be Hycean, there could be many millions of such worlds spread across the Milky Way. Most of them orbit small, dim stars that outnumber stars like our Sun by a wide margin. The thought is humbling. The galaxy may be quietly full of oceans we will never wade into. For tonight, none of this needs to be solved. It only needs to be wondered about. Picture yourself drifting above one of these blue worlds. The hydrogen air is thick beneath you, soft as fog. The ocean below is dark and deep, perhaps tens or hundreds of kilometers down, before it meets whatever lies at the bottom. There are no boats, there are no birds. If anything lives there, it lives in a place no human has ever truly imagined, breathing chemistry we have not yet measured, lit by a sun that does not look like ours. We will sit with this question across the long hours ahead. We will look at how such a world might form, how its weather might move, how its light might filter down through fathom after fathom of warm water. We will look at what we have seen, what we suspect, and what we have argued about. And we will keep returning to the open question at the heart of all of it. Are these worlds common? Are they habitable? Could anything be alive down there in the quiet dark, beneath a sky of hydrogen, in an ocean without a shore? Let us start with the simplest picture, then slowly fill it in. Imagine a planet, somewhere out among the stars. It is larger than Earth, but smaller than Neptune. It has no continents. It has no islands. It has no shoreline of any kind. From pole to pole, all the way around, it is wrapped in a single deep ocean. And above that ocean, instead of the thin blue air we know, there sits a thick, hazy sky, made mostly of hydrogen that, in the gentlest terms, is what some researchers now call a Hycean world. The name itself is a quiet little blend. It comes from the words hydrogen and ocean. A Hycean world, then, is a planet with a hydrogen sky and a water sea. The idea is fairly young. A small team of astronomers proposed it formally in 2021 as a way to describe a class of planets that did not quite fit the older categories. Not rocky like Earth, not gassy like Neptune, something in between, and possibly, just possibly, soft enough to hold liquid water. To make the size feel real, picture Earth growing. Imagine our planet swelling outward until it was about twice as wide. Then a little more. A Hycean world is usually thought to be somewhere between about 1.5 and 2.5 times the radius of Earth. In mass, it might be anywhere from a few Earth masses up to roughly 10. That makes it heavy. If you could somehow stand on a hard surface there, which you probably could not, you would feel a pull stronger than the one you feel right now. Your steps would be slower. Your arms would feel tired sooner. The ocean itself is the part that catches the imagination. On Earth, the deepest trench reaches down about 11 kilometers. That is roughly the height of Mount Everest, flipped upside down and sunk into the sea. On a Hycean world, the ocean might run far, far deeper than that. Some models suggest depths of hundreds of kilometers, maybe even 1,000. The whole of Earth's ocean, every drop of it, would be a thin film by comparison. There is no seabed of rock and sand waiting at the bottom. Instead, the water grows heavier and stranger the deeper you go, until it presses itself into exotic forms we will get to later in the night. The sky above the sea is the other half of the story. On Earth, our atmosphere is mostly nitrogen, with a generous helping of oxygen, and only the faintest trace of hydrogen. On a Hycean world, the balance flips. The air is dominated by hydrogen, with helium mixed in, and small amounts of other gases, such as water vapor, methane, and perhaps ammonia. Hydrogen is the lightest element in the universe. It is also the oldest, born in the first minutes after the universe began. So when you picture the sky, picture something ancient, a blanket of the very first stuff, still wrapped around a world many billions of years later. The thickness of that blanket matters. A heavy hydrogen atmosphere traps warmth in a way our own air cannot. That means a Hycean world could sit much farther from its star than Earth sits from the sun, and still keep its ocean liquid. Some researchers think this could widen the zone where life-friendly temperatures are possible. Others are not so sure, and we will come back to that quiet disagreement in later sections. For now, it is enough to know that a hydrogen sky changes the rules. It stretches the warm region outward and reshapes what we mean when we say a planet is habitable. The ages of these worlds are likely as varied as the stars they orbit. Many of the candidates so far circle small, cool red dwarf stars. Red dwarfs burn slowly, and they live for tens or even hundreds of billions of years. A Hycean planet around such a star could be older than our Sun, or much younger, or somewhere in between. We do not yet have a clean way to date them from across the light years. So that is the basic picture, sketched in soft pencil. A world, larger than Earth, smaller than Neptune, draped in a hydrogen sky, and covered by a single endless ocean, but has no shore. Heavy, hazy, quiet, possibly common, possibly rare, possibly hospitable to something we would recognize as life, or possibly hostile in ways we have not yet imagined. We will keep coming back to that uncertainty all night long. It is the heart of the question. For now, simply hold the image. A deep ocean, a thick hydrogen sky, and a small steady glow on the horizon from a distant cool star. To understand how a Hycean world might come to be, we have to travel back in time, long before any ocean could form, long before any surface could cool. We have to begin with a young star, still gathering itself, still surrounded by a wide, slow disk of gas and dust. This disk is the nursery where planets are born. It spins gently around the star, like a flat, glowing wheel, and within it, small grains begin to stick together. At first, these grains are no bigger than smoke. Over thousands of years, they bump into each other and clump. The clumps grow into pebbles, then boulders, then mountains drifting through the disk. Gravity begins to pull harder as each clump gains mass. Slowly, over millions of years, some of these growing bodies become the seeds of true planets. A Hycean world is thought to begin in this same quiet way. Its rocky and icy core forms first, gathering bit by bit out of the disk. But here is where the story may turn. If the young planet grows fast enough, and if it sits in a cool enough part of the disk, it can begin to pull in the lightest gases of all: hydrogen, helium, the two simplest elements in the universe, left over from the first moments after the Big Bang. This is a delicate balance. A planet that grows too large will keep pulling in gas until it becomes a giant, like Jupiter or Saturn. A planet that grows too slowly will lose the chance to capture much gas at all, ending up small and rocky, like Earth or Mars. A Hycean world, if it truly exists, sits somewhere in between. It must hold on to a thick blanket of hydrogen and helium without becoming so massive that it swallows everything around it. Researchers wonder how often this middle path actually happens. One idea is that Hycean worlds form right where they are found, slowly gathering their atmospheres in place. Another possibility is that they form farther out, in the colder reaches of the disk, and then drift inward over time. A planet drifting toward its star would warm gradually, and any ice it carried could melt into a vast global ocean beneath its hydrogen sky. Both stories are still being tested. The truth may be different for different worlds. Some Hycean candidates may be migrants, others may be locals. We do not yet have enough examples to say which path is more common. The atmosphere itself is part of the mystery. A thick hydrogen envelope is not like the thin air we know. Hydrogen is the lightest gas there is, and it tends to drift away from small worlds. For a planet to keep such an atmosphere for billions of years, it must have enough gravity to hold it, and its star must not strip it away with too much radiation. Red dwarf stars, the small, cool stars that many of these planets orbit, can be both gentle and harsh. They live for a very long time, which is good for stability, but they can also flare, sending out bursts of energy that may slowly peel a hydrogen sky away. So a Hycean world, in its earliest days, may have been a kind of survivor. It had to gather just the right amount of gas. It had to settle into just the right orbit. It had to keep its atmosphere through the wild, flaring youth of its star. And beneath that atmosphere, somewhere along the way, water had to gather and stay liquid. The water itself is another open question. Some of it may have come from the icy bodies that helped form the planet's core. As the young world warmed, these ices could have melted and risen, pooling into a deep global sea. Other water may have arrived later, carried in by comets and frozen wanderers from the outer disk. The exact mix is still being studied, and the answer may shape how we think about the chemistry of these distant seas. What we picture then is a slow and patient birth, a small core gathering in the dark, a blanket of the universe's oldest gases settling around it, a layer of water, deep and quiet, forming somewhere between the rock below and the clouds above. No coastlines, no continents, just sky and ocean and the soft pressure of a hydrogen atmosphere pressing down on everything. Whether such worlds are common or rare, whether they form in place or drift inward from the cold, whether they keep their thick skies for billions of years or lose them slowly to the wind of their stars, these are questions still being asked. For now, we can only imagine the long, gentle work of making such a place, and let our minds rest on the thought of it. Picture, if you will, the slow meeting of two worlds within a single world. Above, a vast canopy of hydrogen and helium, the lightest gases the universe knows how to make. Below, an ocean so deep it has no floor we could ever walk on. And right where these two halves touch, a soft, shifting border of cloud and vapor and falling rain. This is the place we want to wonder about tonight. The seam, the quiet boundary where the sky becomes the sea. To understand what a Hycean world is made of, we have to look far past the planet itself. The hydrogen in its sky is the oldest stuff in the cosmos. Most of it formed in the first few minutes after the Big Bang, when the universe was still a hot, glowing fog. That same hydrogen, drifting for billions of years, gathered into clouds, then into stars, then into the leftover material that becomes planets. When you imagine a thick hydrogen atmosphere swirling around a distant ocean world, you are imagining gas that is nearly as old as time. The helium mixed in with it is almost as ancient. A little of it was forged in the early universe, and a little more is made inside stars, where hydrogen fuses into heavier elements. So the upper sky of a Hycean planet is, in a sense, a museum. Each breath of it carries atoms older than the Earth, older than the Sun, older than nearly anything we can point a telescope at. The water, though, is a different story. Water needs oxygen, and oxygen did not exist in any meaningful amount until the first stars lived and died. Inside those stars, hydrogen fused into helium, helium into carbon, carbon into oxygen, and so on, building the heavier elements one step at a time. When those stars ended their lives, they scattered these new atoms into space. Some of that oxygen later bonded with hydrogen and became water, the same molecule that fills our seas, our clouds, our bodies. So the ocean, on a Hycean world, if it truly exists, may be a quiet record of stellar death. Old stars, broken open, their ashes settling into a warm, dark sea. How that water arrived at the planet is still an open question. One idea is that it formed in place, gathering from the icy grains that drifted through the young planetary disk. Another idea is that much of it was delivered later by comets and icy bodies falling inward from the cold outer reaches of the system. Researchers debate the same puzzle about Earth's own oceans, and the answer for distant worlds may be just as tangled. It is possible that both processes work together in proportions we cannot yet measure from light years away, mixed into the water and the hydrogen sky, we would expect other compounds, though their exact balance remains uncertain. Methane, made of carbon and hydrogen, ammonia, made of nitrogen and hydrogen, carbon dioxide, perhaps, if conditions allow. These molecules give an atmosphere its fingerprint, and they shape the chemistry of any sea below. Some models suggest a Hycean ocean might be gently alkaline, rich in dissolved gases, lightly salted by minerals leached from deeper layers. Other models picture something quite different, more acidic, more strange. We do not yet know which version, if either, is closer to the truth. The minerals themselves, if they exist within reach of the water, would also be borrowed from the deaths of stars. Silicon, magnesium, iron, sulfur, the same elements that built the rocky bones of Earth. On a Hycean world, these may be locked far below, deep beneath crushing pressures, in a layer we will probably never see. But their presence or absence would shape what the ocean can dissolve, what nutrients might drift through it, what chemistry might unfold in its dark middle layers. And so the picture that begins to form is one of deep connection. The hydrogen above came from the dawn of everything. The oxygen in the water came from generations of stars that lived and died long before our sun was born. The carbon, the nitrogen, the sulfur, all of it stitched together from the slow work of the galaxy. A Hycean world, in this sense, is not really a single place. It is a gathering, a meeting, of materials drawn from across cosmic time, arranged into a quiet ocean, wrapped in a quiet sky. Whether anything stirs in that ocean, whether the chemistry there is rich enough to do anything interesting, is a question for later sections. For now, it is enough to picture the ingredients drifting together. Ancient gas above, star-built water below, and between them, a soft pale boundary of cloud, slowly turning in the dim light of afar. Imagine standing at the edge of a Hycean ocean, looking down through the water, wondering what lies beneath. On Earth we know what to expect: sand, rock, sediment, the long slow shelf of a continent. But on a Hycean world, the answer is not so simple. The question of whether these oceans have a solid floor at all is one of the quieter mysteries in this whole story. To understand why, we have to think about the forces pressing down. A Hycean world is wrapped in a thick blanket of hydrogen and helium. Hydrogen is the lightest gas there is, yet there is so much of it that the weight at the bottom becomes immense. Beneath that blanket lies an ocean that could be tens or even hundreds of times deeper than the deepest trench on Earth. Gravity pulls every layer downward. Pressure builds with each kilometer of descent somewhere far below the waves. The pressure grows so great that water no longer behaves the way we know it. It does not freeze the way ice cubes freeze in a freezer. It does not boil into steam the way a kettle boils. Instead, it enters strange high-pressure phases. Some researchers think that deep water might become a kind of warm, dense ice, solid, but nothing like the ice you would skate on. Others think it might stay liquid, just incredibly compressed, with properties closer to a thick syrup than to anything we splash in. If that high-pressure layer forms, it could act like a floor of sorts, not rock, not sand. A floor made of water itself, pressed so hard it has become a different substance. Below that, deeper still, would be the planet's true rocky core, hidden beneath a shell of strange ice that might be thousands of kilometers thick. Whether the liquid ocean ever touches that rock directly is one of the great open questions. This matters more than it might first seem. On Earth, life depends on minerals leaching from rock into the sea. Hot vents at the bottom of our oceans feed strange creatures with chemistry pulled from the planet's interior. If a Hycean world has a thick layer of high-pressure ice separating the liquid ocean from the rocky core, that mineral exchange might be blocked. Some scientists wonder if life could still thrive without it. Others suspect that without a stone floor in contact with the water, the chemistry of life would have a much harder time getting started. There is another view. Some models suggest that on smaller Hycean worlds, or on those with less water, the ocean might sit directly on rock after all. In that case, vents and minerals and warmth could rise from below, much as they do on Earth. The thickness of the ocean, the mass of the planet, the heat coming from its interior, all of these change the answer. We do not yet know which kind of Hycean world is more common, or whether the most promising candidates we have found so far have a rocky floor or an icy one. Heat plays its own quiet role in all of this. A Hycean planet holds onto warmth from its formation, slowly leaking it outward over billions of years. Radioactive elements deep in the core add a little more. That gentle inner heat could drive slow currents through the deep ocean, stirring it from below. If there is a rocky floor, those currents might carry minerals upward. If there is an ice floor, the heat might still create motion, but the chemistry would be far quieter. Tidal forces also press on these worlds. Many Hycean candidates orbit close to small, cool stars. The star's gravity tugs unevenly on the planet, flexing it gently, generating a little extra warmth from inside. This could keep the deep ocean stirred and the inner layers active, or it could be too weak to matter much. The strength depends on the orbit, the size of the star, and the structure of the planet itself. Magnetic fields are another puzzle. A hydrogen atmosphere, this thick, sitting above a deep ocean, would respond strangely to any magnetic field the planet generates. We do not know how strong those fields would be, or whether they would shield the ocean from the radiation of the parent star. On worlds orbiting red dwarfs, that shielding could matter a great deal. So when we picture a Hycean sea, we should hold the picture loosely. The floor might be stone. It might be a strange warm ice. It might lie so deep that no light, no current, no mineral ever reaches it. The forces are real. The structure they sculpt remains unknown. And we drift, for now, above a question with no certain bottom. To feel the scale of a Hycean world, it helps to start somewhere familiar. Stand at the edge of a swimming pool. The water at the bottom presses against your ears at about 1.5 times the pressure of the air around you. A swimmer 30 feet down feels twice that. A diver 100 feet down feels 4 times the weight of the sky. Now imagine, instead of a pool, an ocean, not the kind Earth has, but one that could be hundreds of kilometers deep, with no floor of sand or rock waiting at the bottom. Just water, growing darker and heavier with every meter you sink. On Earth, the deepest spot we know is the Challenger Deep, almost 11 kilometers beneath the waves. The pressure there is about 1,000 times what you feel at sea level. A styrofoam cup, sent that deep, comes back the size of a thimble. Now picture sinking 10 times deeper than that. Then 100. On a Hycean world, the ocean may stretch downward further than the entire diameter of the moon. That is the scale researchers are quietly wrestling with when they sketch these planets. The sky on such a world adds its own weight. Earth's atmosphere presses down with what we call 1 bar, the same gentle hug you feel on your shoulders right now as you rest. A Hycean atmosphere, thick with hydrogen, could press down with 10 bars, 50 bars, perhaps more. Some models suggest the air at the ocean's surface might feel like the water pressure 100 meters down, in one of our own seas. The surface itself would be a place where air and ocean blur. The hydrogen above is so dense, the water below so still, that the line between them softens. Try to picture standing at that surface, if standing were possible. The sky would not feel like a sky. It would feel like a slow blue-grey sea above you, pressing on your chest with the weight of a small car. And below you, the ocean would continue down farther than light has any chance of reaching. The deepest sunlight on Earth fades to black at about a kilometer on a Hycean world. The last photon might give up far sooner, swallowed by clouds and haze long before it touches water. The numbers grow stranger the deeper you go. At the bottom of a 200-kilometer ocean, the pressure could reach tens of thousands of bars. That is more than the pressure at the center of our own planet's mantle near its upper edges. Water under that kind of squeeze does not behave the way it does in your kitchen sink. It becomes something else. Some researchers think it could shift into exotic forms. Ice that is hotter than boiling water, held solid only by the crushing weight above. Others think the bottom might never form a true solid layer at all, just a slow, thick transition from liquid to something denser, with no clear edge. The truth depends on the planet's exact temperature, and we do not yet know those temperatures for any single world. If you shrunk a Hycean planet to the size of an orange, the ocean would be a skin around it, about as thick as the peel. The hydrogen sky above would be a hazy bloom, another peel thick. The rocky or icy core, if there is one, would be a hard pit at the center, smaller than you might expect. Most of what makes the planet a planet would be fluid. There is nothing in our own solar system quite like it. Neptune has hydrogen and water, but it is colder and stranger. Earth has oceans, but they are thin films on stone. A Hycean world would be ocean almost all the way down. The temperature scale matters too. The surface might sit near the comfort of a warm bath, perhaps 30 or 40 degrees Celsius in some models, but descend a few hundred kilometers, and the heat could rise past anything a human body could imagine. Hot enough to glow if it were not for the pressure keeping the water dense and dark. Whether anything could survive in the narrow band near the top, where light might still flicker through and warmth still feels gentle, is one of the questions researchers cannot yet answer. The habitable layer, if it exists, might be a thin shell only tens of kilometers thick, floating above an enormous, unreachable deep. It is a scale that resists easy comparison. A world with more water than rock, more sky than land, and pressures that climb from a soft breath at the top to something almost beyond imagining at the bottom. We are only beginning to picture it. Imagine, for a moment, that you could drift down through the upper layers of a Hycean world. Picture yourself slowing as you fall, suspended in a soft veil of gas, watching the colors of the sky change around you. The light here would not behave the way light behaves on Earth. It would arrive through a deep, heavy ocean of air, and that ocean would shape every shade you saw. High up, near the top of the atmosphere, the sky might look thin and almost colorless. The hydrogen and helium that make up most of this air are nearly transparent to visible light. A small red sun, low and patient on the horizon, would shine through these upper layers with a soft amber tint. The stars beyond might still be faintly visible during the day, glimmering through a sky that feels less like a ceiling and more like an open window. As you sink lower, the air would thicken, light would begin to scatter, pale haze. Layers might stretch out in long ribboned bands. Some researchers suggest these worlds could carry thin clouds of water droplets, at certain altitudes. Others wonder if the hazes might be made of simple organic molecules, formed when starlight breaks apart traces of methane in the upper air. We do not know for certain. Both ideas remain on the table, and both would paint the sky in different tones. If the hazes were rich in organic compounds, the upper atmosphere might glow with a dusty orange. Sunsets could last for hours, stretched by the slow rotation many of these worlds may have. If, instead, the upper sky were clearer, the dominant color might lean toward a quiet, washed blue, shaped by the way short wavelengths scatter through dense hydrogen. The truth probably sits somewhere between these guesses, varying from one Hycean world to the next. Lower still, the air would press in around you. Light, reaching this depth, has been filtered, softened, and bent. The reds and oranges might travel farthest, while the blues and violets would have scattered away long ago. The world below would take on a warm, dim glow, like the inside of a candlelit room. Shadows would be soft, edges would blur. There would be no sharp line where the sky ends and the ocean begins. The air simply grows heavier and heavier until, somewhere far below, it touches the surface of the sea. That surface itself is one of the strangest parts to picture. Without continents, without islands, without any rock breaking the horizon, the ocean would stretch in every direction in a single unbroken sheet. Its color is something we can only guess at. If the water held dissolved organic material, it might appear a deep tea brown. If it remained clean and clear, it might mirror the muted sky above, glowing a soft rust or honey under a red dwarf sun. Some theorists think the surface could be dotted with patches of foam, churned up by storms that never quite end. The horizon on such a world would feel different too, with a thick atmosphere bending light around the curve of the planet. The edge of the sea might appear lifted, almost as if the ocean were rising to meet the sky. Distant clouds could seem to float higher than they really are. Mirages would be common. A floating observer might see a second, ghostly horizon shimmering above the first, a trick of refraction in dense, warm air. Above, the clouds themselves remain a quiet puzzle. On Earth, clouds form sharp white shapes against a blue background. On a Hycean world, the contrast might be far gentler. Some models suggest the clouds would sit in thick layered sheets, more like fog banks stacked on top of one another. Others propose patchier weather, with open windows of clearer air between drifting clusters of vapor. Both pictures might be correct for different planets, or even for different regions of the same planet. We simply do not yet know. What we can say is that this is not a world of harsh contrasts. There would be no blinding glare, no crisp shadows, no bright noon. Everything would feel softened, hushed, like an afternoon seen through colored glass. The sun would be a gentle ember. The sea would be a slow mirror. The sky would hold its warm haze close to itself, hour after hour, with no sudden changes. Whether anyone, anything, could ever look up at that sky and wonder back at us is a question we cannot yet answer. For now, we are left only with the picture: a still ocean, a heavy glowing air, a small red sun easing toward a horizon that may never quite finish setting. Imagine standing on a small raft made of light, drifting just below the surface of one of these worlds. Look up, and the sky above the water would not be the pale blue we know from home. It would be something else entirely, something we have only begun to picture in our minds. The color of a hydrogen sky is one of the quiet puzzles of these ocean planets, and the answer depends on layers most of us have never thought about. Hydrogen, on its own, is nearly invisible to the human eye. It does not scatter light the way nitrogen does in our own atmosphere. So a pure hydrogen sky, in theory, could look strangely clear, almost colorless, the stars perhaps still faintly visible during the day. But no Hycean atmosphere is pure hydrogen. There are traces of methane, water vapor, ammonia, and other molecules mixed in. Each of these touches the light in its own way, bending it, absorbing certain colors, letting others pass through. Some models suggest a soft, hazy sky tinted in warm honey tones, where methane drinks up the redder light and leaves a muted gold above the waves. Other models picture something closer to a deep, smoky blue, where high clouds of unknown chemistry scatter the bluer wavelengths back down towards the ocean. A third possibility is a sky almost the color of weak tea, dimmed by particles of organic haze drifting slowly in the upper layers. We do not know which of these pictures is right. We may not know for a long time. Below the surface, the colors shift again. Sunlight from a cool red star, filtered through hundreds of kilometers of dense hydrogen, would already be soft and reddened by the time it touches the water. As it sinks into the ocean, the water itself absorbs the longer wavelengths first. Red fades quickly, then orange, then yellow. What remains, deeper down, might be a tired green or a slow fading blue. And below that, eventually nothing at all. A darkness so complete that the idea of color loses meaning. The depth at which light disappears in a Hycean world is one of the open questions researchers think about. On Earth, sunlight in clear ocean water can still be faintly detected at around 1,000 meters. On a Hycean world, the atmosphere above the water is so thick that less light may reach the surface to begin with. Some estimates suggest a permanent twilight, even at noon, a gentle dimness that never brightens into full day. Others suggest that under a clearer hydrogen sky and a closer star, the surface might be brighter than we expect. Neither picture has been confirmed. The question of color matters more than it first seems. If anything lives in such an ocean, the wavelengths of light that reach it would shape the chemistry of that life. On Earth, plants are green because they use the red and blue parts of sunlight and reflect the green back. On a world bathed in reddened, filtered light, photosynthesis, if it exists at all, might use different pigments entirely. Some researchers wonder if such life could look black or deep purple or a dusky orange, soaking up every photon it can find. Others wonder if photosynthesis is even possible under such a heavy atmosphere. The light may simply be too weak by the time it reaches anything alive. Deeper still, beyond the reach of any starlight, the ocean would be lit only by whatever the planet itself produces. Faint glows from chemical reactions, the slow shimmer of heat rising from below. Perhaps, if the world is geologically active, the soft red light of vents on the floor, glowing where hot water meets cold. These are speculations, of course. We have no images, no measurements, no recordings of sound from such a place. We only have the chemistry, the physics, and the patient work of imagining what such a depth might look like. What stays with you, sitting with this idea, is how much of it remains unwritten. The color of a Hycean sky has never been seen by human eyes. The shade of its deep ocean has never been measured by any instrument. Every guess we make is built from the light of distant stars, gathered by telescopes, sifted through equations. The picture we hold in our minds is only a sketch, drawn in the faintest pencil, waiting to be filled in. Somewhere out there, a sky we have not yet named arches above a water we have not yet touched. Its color is real, even if we cannot see it. It is simply waiting, quiet and patient, for the slow work of discovery to catch up to it. Every world we know moves to a rhythm. The Earth turns once a day, it circles its star. Once a year, the moon pulls the tides up and down along our shores. Ice ages come and go. Even the sun breathes in its own slow way, brightening and dimming on a cycle of about 11 years. Cycles are the heartbeat of any habitable world. So if Hycean planets are real, they too must have their own rhythms. The question is, what those rhythms look like beneath a sky of hydrogen. Many of the candidate Hycean worlds orbit red dwarf stars. These are the small, cool, long-lived stars that make up most of the galaxy. A red dwarf burns slowly and gives off less light than our sun. To stay warm enough to keep liquid water, a planet must huddle close to its star. That closeness changes everything about its cycles. A year on such a world might last only a handful of Earth days. The planet rushes around its star, while the star itself drifts through space, in no particular hurry. Living close to a small star brings another effect. Gravity from the star can lock the planet's rotation, so that one side always faces the star, and the other side faces forever into the night. Researchers call this tidal locking. We see it with our own moon, which always shows Earth the same face. If a Hycean world is tidally locked, then it has no sunrise and no sunset. Its day side bakes under steady red light. Its night side sits in cold, endless dark. The cycle of day and night, so basic to life on Earth, may not exist there at all. That raises a quiet question. Could such a world still be habitable? One idea is that the thick hydrogen atmosphere would carry heat from the day side to the night side in great slow winds. The ocean below would do the same with deep, broad currents. Warm water would flow toward the cold half of the planet. Cold water would creep back beneath it. In this view, the whole world becomes one giant heat engine, smoothing out the difference between bright and dark. A competing view is more cautious. Some models suggest that the night side could grow cold enough for the hydrogen itself to behave strangely, or for thick clouds to form a barrier that traps heat unevenly. Which picture is closer to the truth? We cannot yet say. Even without a day and night cycle, other rhythms remain. The star itself is not perfectly steady. Red dwarfs are known for their flares, sudden bursts of light and high-energy radiation that can last minutes or hours. Some of these stars flare often, others go quiet for long stretches. A Hycean world might feel its star calm for weeks, then bright and angry for an afternoon. The thick atmosphere likely shields the ocean below from the worst of these flares. Hydrogen and water vapor absorb a great deal of harmful radiation before it can reach the depths. Still, the upper air would heat and stir with every outburst, sending pulses of warmth downward. Then there are the tides on Earth. Tides are gentle visitors. On a close-in Hycean world, tides could be steady and strong, raising long, slow swells across the global sea. If the planet has a companion, a moon, or a sibling planet in a nearby orbit, those tides could rise and fall on a regular beat. The ocean would breathe in and out, never reaching a shore, only sloshing against itself across thousands of miles of open water. We do not yet know if any candidate Hycean world has a moon. The signal would be very faint, far below what current telescopes can detect. Longer cycles may matter even more. Stars change over billions of years. A red dwarf grows slightly brighter as it ages, and its habitable zone slowly shifts outward. A planet that begins its life as a warm Hycean world might, over vast stretches of time, become too hot. Its hydrogen might start to escape into space more quickly. Its ocean might begin to evaporate from the top. Some researchers think this slow drying could leave behind something closer to a rocky super-Earth. Others suspect the atmosphere is more stable than that, holding on for many billions of years. The truth almost certainly varies from planet to planet, so the cycles of a Hycean world remain mostly hidden from us. We can guess at warm currents and slow tides, at flares and aging stars, at oceans that breathe without ever touching land. We can sketch the rhythms in theory. The real song of such a world, if there is one, still plays far out of earshot. No world drifts entirely alone. Every ocean planet, wrapped in its thick hydrogen sky, belongs to a family of objects, a quiet gathering of bodies that share a star, a history, a slow choreography of orbits. To wonder about a Hycean world is to wonder about its neighbors too, the planets beside it, the star above it, the cold edge of the system far beyond. In the catalogue of known exoplanets, the candidate Hycean worlds tend to live close to small, dim stars called red dwarfs. These stars are smaller and cooler than our Sun. They burn slowly, patiently, sometimes for trillions of years. Around such a star, the warm region where liquid water might exist sits much closer in than it does around the Sun. A Hycean world might orbit there in just a few weeks, or even just a few days, sweeping around its quiet red sun, again and again, while we, far away, watch for the smallest dip in starlight. Often these worlds are not alone in their system. Astronomers have found packed planetary families around red dwarfs, with 3, 4, sometimes 7 worlds threaded together in close orbits. A candidate Hycean planet might have rocky cousins inside its orbit, baked and dry, and icy cousins further out, dim and slow. The whole system can fit inside the orbit of Mercury. It is a tight, intimate arrangement, and the planets tug on each other gently as they pass. That gentle tugging matters. Gravitational nudges between neighbors can stretch and squeeze a planet's orbit, making it slightly oval instead of perfectly round. A stretched orbit means the planet moves closer to its star and then further away in a rhythm. That rhythm can flex the planet's interior, generating heat from friction deep inside. On a Hycean world, this hidden warmth might stir the ocean from below, mixing deep water with shallow water, carrying minerals up from whatever lies at the bottom. Or it might do almost nothing at all. We do not know yet how strong these tidal effects would be on such large watery planets. The star itself is a complicated neighbor. Red dwarfs are famous for being moody. They can sit calmly for long stretches, then release sudden bright flares of radiation. A flare from a red dwarf can be thousands of times stronger than anything our Sun produces. Some researchers wonder whether a thick hydrogen atmosphere could shield a Hycean ocean from these flares, acting like a deep, soft blanket. Others worry that repeated flares might slowly strip the atmosphere away, peeling off the hydrogen layer over millions of years until the ocean lies exposed, or boils, or freezes. Which picture is closer to the truth depends on details we cannot yet measure. There are other neighbors too, further out. Many of these systems likely have belts of icy debris in their cold outer reaches, left over from the early days of planet formation. Pieces of that debris can fall inward over long stretches of time. A Hycean world might be visited now and then by a slow rain of icy bodies arriving from the dark edge of its system. Each impact would carry water, carbon, perhaps simple organic molecules, dropped quietly into the global sea. Whether this gentle delivery enriches the ocean or barely changes it is another open question. The wider neighborhood matters in a different way as well. The galaxy itself is full of red dwarf stars. They are by far the most common kind of star we know of. If Hycean worlds form easily around them, then this strange class of planet, global ocean, hydrogen sky, No shore anywhere might be one of the most common habitable settings in the Milky Way, more common, perhaps, than worlds like Earth. That is a striking thought to sit with. Our familiar blue planet, with its continents and clouds, might be a rare arrangement, while the more typical living world, if living worlds are common at all, might look nothing like home, or it might be the other way around. Some researchers argue that what we are calling Hycean Worlds might really be mini Neptunes with crushing pressures and no liquid ocean at all. In that view, the watery cousins are the rare ones, hidden among many lookalikes. The neighbors all wear similar clothing from a distance, and we cannot yet tell which is which. So a Hycean world, if it exists, lives in good company, a patient red star, rocky and icy siblings, distant ice belts, and, somewhere in the same galaxy, perhaps countless others like it, quietly turning beneath their soft hydrogen skies, waiting for our instruments to grow patient enough and sharp enough to truly see them. Picture a world where the wind has nothing to push against. No mountains, no coastlines, no forests, only ocean, stretching in every direction, and above it, a sky thick with hydrogen and helium, reaching far higher than any sky we know. On a world like this, the storms would not behave the way ours do. They would be born differently, travel differently, and possibly last for lengths of time that stagger the imagination. On Earth, storms break when they hit land. They wear themselves out against mountains, against forests, against the rough edge of a continent. A hurricane that crawls onto shore loses its engine within hours. But on a Hycean world, if such worlds truly exist, there is no shore. A storm could circle the entire planet, gathering strength as it spins, fed by warm water below and cool hydrogen above, with nothing in its path to slow it down. Some researchers wonder whether the strongest of these storms might persist for years, even centuries. The great storm on Jupiter, the swirling oval that has churned for at least 400 years, gives us a hint of what a hydrogen atmosphere can do. Jupiter has no surface to interrupt its weather, and so its storms simply keep going. A Hycean world, smaller and gentler, might still inherit some of that same persistence. The question of how long a storm can live on such a planet remains open. The wind speeds are harder to guess. On the gas giants closer to home, winds can race at hundreds of meters per second. Neptune, the bluest and most distant of our giants, hosts some of the fastest winds in the solar system, despite sitting so far from the sun that it barely feels warmth at all. A Hycean world, warmer and wetter, might be calmer, or it might be wilder. We simply do not know. The rain on such a world would be something else entirely. Under a thick hydrogen sky, water droplets would form in clouds far above the ocean surface, then fall through layers of dense hazy air. The droplets might be large, slow, and heavy, or they might evaporate before they ever reach the sea, recycled endlessly between cloud and sky. Some models suggest that the lowest layers of the atmosphere could be so humid that the boundary between ocean and air becomes blurred, a soft transition rather than a clean edge. Lightning is another puzzle. On Earth, lightning needs ice crystals and water droplets to rub together and build up charge. On a Hycean world, the chemistry of the clouds would be different. Hydrogen does not store charge the same way nitrogen and oxygen do. Yet, on Jupiter and Saturn, lightning still flashes, sometimes brighter than anything we see in our own skies. If a Hycean world has lightning, it might illuminate the underside of clouds in flashes that travel for thousands of kilometers, with no one and nothing to witness them. Then there is the matter of heat. A thick hydrogen blanket traps warmth far more efficiently than Earth's thinner air. A Hycean world, orbiting at the cold edge of its star's habitable zone, might still have a temperate ocean, kept warm by the heavy sky pressing down, but this same blanket means that any heat released by a storm has nowhere quick to go. Energy could build up in the atmosphere, releasing itself in long, slow pulses, rather than the sharp bursts of an earthly thunderstorm. The largest storms might also reshape the chemistry of the air around them. Powerful updrafts could lift water vapor high into the hydrogen layers, where sunlight would break it apart into oxygen and hydrogen atoms. Some of that oxygen might bond with carbon to form new compounds. Some might drift upward and slowly escape into space. The atmosphere of a Hycean world might be in constant, slow chemical motion, stirred by storms we cannot see. A competing view holds that Hycean worlds might be far calmer than the gas giants suggest. Because their oceans are liquid, not gaseous, the surface could act as a kind of stabilizer, absorbing energy and smoothing out the wildest swings. In this picture, a Hycean sky might be hazy and steady, with broad, slow weather patterns rather than violent storms. The truth probably depends on the size of the planet, the distance from its star, and the depth of the ocean below. For now, we can only sketch these extremes in our minds. Storms that circle a world forever, lightning that no eye has ever seen, rain that may never reach the sea. Somewhere out among the stars, such a sky might already be turning, slow and heavy, above an ocean that has no shore to find. Imagine slipping beneath the warm upper layer of a Hycean sea, past the gentle swirl of waves, into the long, slow body of water below. On Earth, oceans churn in patterns we have spent centuries learning to read. Warm water rises near the equator. Cold water sinks near the poles. Great rivers of current loop around the globe, carrying heat from one hemisphere to the other. On a Hycean world, these patterns might exist too, but in shapes we can only guess at. The first quiet detail is the matter of depth. Earth's ocean averages around 4 kilometers deep. A Hycean ocean could be hundreds of kilometers deep, possibly more. There may be no true flaw in the way we picture it, only water giving way slowly to ice of a strange high-pressure kind. So a current here would not bounce off a continental shelf or curl around an underwater mountain. It would simply keep going, turning in long, lazy gyres that take a very long time to complete. Some researchers think these deep currents would move slowly. Others suspect that under a thick hydrogen sky, with strong heating from above and cooling further down, the water might churn more vigorously than we expect. The honest answer is that we do not yet know. The math of ocean circulation depends on details we cannot measure from light years away. The salt content, the dissolved gases, the temperature at every depth, all of these remain hidden. A second small wonder lies in the chemistry of the water itself. Earth's oceans taste of salt because rivers have been carrying minerals from the land for billions of years. A Hycean world has no land. There are no rivers grinding down mountains, no dust blowing off deserts, no volcanoes pushing fresh rock to the surface. So the chemistry of that endless sea might be very different. Some models suggest it would be unusually pure, with only the gases of the atmosphere dissolved into it. Others suggest that minerals from the deep interior could seep up through the high-pressure ice layer, slowly seasoning the water from below. Which picture is closer to the truth? No one yet knows. Consider also the question of color. Light filters through a hydrogen sky differently than it does through ours. Our atmosphere scatters blue light, which is why our daytime sky looks the way it does. a hydrogen-rich atmosphere, much thicker and denser, would scatter and absorb light in its own unique way. The water beneath might glow with a hue we have no name for, perhaps a deep teal, perhaps a soft slate grey, perhaps something stranger. From orbit, the planet might appear a muted blue, a pale violet, or a soft cream, depending on the haze above. We have only the faintest hints in current data. There is a quieter detail still. On Earth, when wind blows across water, it stirs the surface and mixes oxygen into the upper layer. On a Hycean world, the winds in that thick hydrogen sky would push down on the surface with great force. The waves they make might be tall and slow, rolling for thousands of kilometers without breaking against anything. A single wave could travel half the world before fading. Beneath all of this, scientists wonder about another subtle pattern, the way heat moves from the warm day side to the cool night side on a tidally locked world. If a Hycean planet always shows the same face to its star, the ocean might carry heat around the globe in a slow underwater conveyor. That flow would soften the temperature difference between day and night, keeping the cold side from freezing solid. One theory says the ocean does most of the work. Another says the atmosphere does. The truth is likely a mix, but the balance remains uncertain. Then there is the matter of sound. Water carries sound far more efficiently than air. In Earth's oceans, low rumbles from distant storms can travel across entire basins. On a Hycean world, with so much more water and no continents to break up the path, a single deep note might circle the planet again and again, fading only slowly. It is a strange thought that somewhere out there, an ocean might hum with sounds that have been traveling for years. These details are the kind scientists savor. They are the textures of a world we may never visit, sketched in equations and educated guesses. The grand picture of a Hycean ocean is fascinating on its own. The quiet details, the colors and currents and slow waves and humming depths are what make it feel like a real place. A place where perhaps something is drifting in the dark, listening to a sound that has crossed an entire world to reach it. The story of how we came to suspect that worlds like these might exist is a slow one, built from many small steps rather than a single bright moment. For most of human history, the only planets we knew were the ones in our own sun's family. 8 of them, give or take, all visible through telescopes that grew slowly more powerful across the centuries. None of them were ocean worlds blanketed in thick hydrogen. None of them were anything like the strange middle-sized planets we now believe fill the galaxy. The first hint that other stars had planets at all came in the early 1990s. Astronomers found small worlds orbiting a dead stellar core, and a few years later, a giant planet swinging close around a sun-like star. These early finds were not gentle blue oceans. They were hot gas giants and broken remnants. Yet they cracked the door open. If one star had planets, perhaps every star did. And if every star did, the variety out there might be wider than anything our solar system showed us. The real flood came with space telescopes built to stare at single patches of sky for months at a time. They watched for tiny dips in starlight, the faint shadow of a planet crossing in front of its star. From those dips, astronomers could measure how big each planet was. A surprise emerged from the data. Many of the most common planets in the galaxy were sized between Earth and Neptune. There was nothing like them at home. We had no name ready, no model prepared. We simply called them sub-Neptunes, or super-Earths depending on which side of the gap they fell on. For a long time, no one knew what these worlds were made of. Their size alone could not tell us. A planet 2 or 3 times the width of Earth, might be a rocky ball with a thin skin of air, or a small gas giant with no surface at all, or something else entirely. The density helped a little. Some of these worlds were too light to be solid rock, and too heavy to be pure gas. That middle ground hinted at thick atmospheres, deep ices, or perhaps oceans far larger than any on Earth. The word Hycean entered the conversation only recently, in the early 2020s. A team of researchers working on planet models proposed it as a name for a specific kind of world. The idea was simple, even if the planet itself would be anything but. Take a sub-Neptune, give it a deep global ocean of liquid water, wrap that ocean in a thick atmosphere of hydrogen under the right conditions. Such a planet could stay temperate across a much wider range of distances from its star than a rocky world ever could. It was a theory, nothing more, but it gave astronomers a target shape to look for. The way we read the chemistry of these distant atmospheres is itself a small marvel. When a planet passes in front of its star, a thin sliver of starlight filters through the planet's air on its way to us. Different gases absorb different colors of that light, leaving dark gaps in the spectrum. By measuring the gaps, astronomers can guess which gases are present. The method is called transmission spectroscopy. It is delicate work. The signals are faint, the stars are noisy, and the planets are far away. A single measurement can take dozens of hours of telescope time. Sometimes more. Older space telescopes manage to pick up water vapor in the atmospheres of a few sub-Neptunes. That was already a quiet triumph. Water on a world many light years from ours, detected by the soft fingerprint it left in starlight. But water alone did not prove an ocean. It might sit as vapor in a hot upper layer, with nothing liquid below. Researchers argued, and still argue, about how to tell the two cases apart. When the James Webb Space Telescope began its work, the chemistry it could read grew far richer. It could pick out methane, carbon dioxide, and other molecules at concentrations earlier instruments would have missed. The early results stirred excitement and caution in equal measure. Some teams reported hints of molecules that, on Earth, are often linked with living things. Other teams looked at the same data and saw something thinner, less certain. The debates are open. They may stay open for years. What is clear is that the idea of a Hycean world did not arrive in a flash. It grew, slowly from decades of patient watching, spectra by spectra, dip by dip, a name proposed, a theory built, and a sky full of candidates still waiting to be understood. The strangest part of studying these distant ocean worlds is that we never actually see them. Not really. We see their stars. We watch a tiny dip in starlight as a planet crosses in front of its sun, and from that small shadow, we try to read entire worlds. This method has a quiet name. It is called transmission spectroscopy, and it works by catching the thin sliver of starlight that filters through a planet's atmosphere during a transit. That sliver of light is the whole conversation. Every gas in the atmosphere leaves a fingerprint on it. Water vapor absorbs certain colors. Methane absorbs others. Hydrogen leaves its own pale signature. By spreading the starlight into a spectrum and looking for the missing bits, we can guess what the air around a faraway world might contain. The light has often traveled for more than 100 years before reaching us, and only a hair-thin band of it ever touched the planet at all. What surprises many people is how little light we are actually measuring. The atmosphere of a planet orbiting a distant star blocks only a tiny fraction of a percent of the star's brightness. The signal we hunt for is sometimes smaller than the flicker of the star itself. To pull a clear answer from such a faint whisper, telescopes have to stare for hours, Repeat the measurement across many transits and compare the results with great care. Stranger still, the part of the atmosphere we can read is not the surface, it is the top. The light grazes only the highest, thinnest layers of gas, where the air begins to thin into space. For a Hycean world, that means we mostly learn about the upper hydrogen envelope. The ocean below remains hidden, sometimes by thousands of kilometers of cloud and haze. The water we are most curious about lies far beneath the only window we have. This leads to a quiet, counterintuitive truth. A planet can be drenched in liquid water and still appear to our instruments as a hydrogen world. The ocean itself does not send us a signal. We can only infer it from the chemistry of the air above. If the upper atmosphere holds water vapor in the right amounts, alongside methane, carbon dioxide, and a few other clues, some researchers argue that a deep ocean is the simplest explanation. Others wonder if the same fingerprints could come from a planet with no ocean at all. Just a deep, soupy sky. The surprises keep coming. Clouds can mute the entire signal. A thick layer of haze high in the atmosphere can flatten the spectrum until almost no features show. Two planets with very different chemistries can look nearly identical from our distance, simply because their upper clouds happen to match. This is one reason the chemistry of Hycean candidates remains contested. The data is real, but the reading of it is delicate. There is another quiet wrinkle. The star itself can fool us. Cool red stars, the kind most Hycean candidates orbit, are covered in dark spots and bright patches. When a planet crosses in front of an unspotted region, the spectrum looks one way. When it crosses a spotted region, the same planet can look different. Some signals once thought to come from a planet's atmosphere may have been the breathing of the star instead. Researchers are still working out how to tell these effects apart. The most counterintuitive surprise of all may be that biology, if it exists in these oceans, might be easier to detect than the oceans themselves. Certain molecules produced by living things float upward and mix into the upper atmosphere. They can leave fingerprints even when the water below stays invisible. A whole sea could be hidden from us while a single trace gas, in tiny amounts, hints at what swims beneath. Whether any such gas has truly been seen yet is still an open and lively debate. What does seem clear is that we are reading these worlds through a very narrow keyhole. The hydrogen sky is the page we get to study. The ocean is a line we have not yet learned to read. Every measurement is a careful guess built on a faint shimmer of color in starlight that left its home long before our instruments existed to catch it. Sit with that for a moment as you drift. Somewhere, right now, light is leaving a star and threading through the upper air of a distant ocean world. In a few decades, it will reach a telescope not yet built. Someone, perhaps not yet born, will look at that thin sliver of color and wonder, as we are wondering tonight, what lies beneath the clouds. Among all the planets we have studied from afar, one has come to stand at the center of the Hycean conversation. Its name is K2-18b, and it orbits a small, cool red dwarf star, about 120 light-years from us, in the direction of the constellation Leo. It is a little more than 8 times the mass of Earth, and a little more than 2 times its radius. That places it squarely in the strange middle zone between rocky worlds like ours and small gas giants like Neptune. And it sits within the temperate band of its star, where liquid water might be possible. K2-18b is not a Hycean world by proof. It is a Hycean world by suggestion. The data we have gathered hint at a thick hydrogen atmosphere with methane and carbon dioxide mixed in. The combination is interesting because it matches what some models predict for a planet with a deep ocean beneath a hydrogen sky. But other models predict the same chemistry for a small gas world with no ocean at all. The signal alone cannot tell us which picture is right. The mystery deepened when in 2023, a team using the James Webb Space Telescope reported a faint hint of a molecule called dimethyl sulfide in K2-18b's atmosphere on Earth. That molecule comes almost entirely from ocean life, from tiny plankton drifting in sunlit seas. If the detection holds, it could be one of the first whispers of biology beyond our solar system. If it does not hold, it would simply be noise in the data, or a molecule produced by chemistry we do not yet understand. The team itself called the result tentative. Other researchers have since looked at the same data and disagreed about whether the signal is really there. This is where K2-18b connects to the larger puzzle. The planet is not just one curious world. It is a test case for an entire class of worlds. If we can learn to read its atmosphere with confidence, we can begin to read others. The same techniques will apply to dozens of similar planets that have already been catalogued and to hundreds more waiting to be found. The connection runs deeper than instruments. K2-18b orbits a red dwarf, and red dwarfs make up roughly 3 out of every 4 stars in the galaxy. These small stars burn slowly and live for trillions of years. Their habitable zones sit close in, where planets can become tidally locked, always showing the same face to their sun. A Hycean world in such an orbit would have one hemisphere in eternal day and another in eternal night, with a thick hydrogen blanket carrying heat from one side to the other. Whether that blanket would smooth the temperatures gently or whip itself into endless storms is something simulations still argue about. The star itself shapes everything below. Red dwarfs flare often, sending bursts of radiation outward. A thick hydrogen atmosphere would shield the ocean from much of this, like a soft grey ceiling above the waves. But over billions of years, that same radiation slowly strips the upper layers of the atmosphere away. The hydrogen leaks into space, drop by drop, so a Hycean world might only stay Hycean for part of its life. Earlier, it could have been more like a small Neptune. Later, it could become a bare, rocky world with no air at all. Where K2-18b sits in that long arc we do not know. The ocean below, if it exists, would feel all of this from a great distance. Starlight, filtered through hydrogen and methane, would reach the surface as a dim reddish glow. Heat from the atmosphere above, and possibly from the rocky core below, would set up slow currents in the water. Volcanic activity, if any rocky floor lies deep beneath the sea, could release minerals and gases that mix into the global ocean over millions of years. Each of these processes would leave fingerprints in the atmosphere we observe from afar. Small shifts in chemistry that tie the world below to the sky above. That is why K2-18b matters even if the dimethyl sulfide signal fades. The planet is a single note in a much larger song. Its star, its orbit, its size, its chemistry, and its possible ocean are all linked. To understand one Hycean candidate is to begin understanding how stars, atmospheres, oceans, and possibly life weave together across the galaxy. For now, the threads are loose. We see the shape of something, but not its details. K2-18b waits patiently, far away, holding its answer just beyond the edge of what we can yet see. K2-18b is only one name in a much longer list. As our telescopes have grown sharper, the catalogue of possible Hycean worlds has slowly filled with quiet cousins, each one a little different, each one raising the same gentle question in a slightly new way. The list keeps changing. A planet that looked like a small gas world 5 years ago might be reclassified next year as a possible ocean world. Another that seemed promising might fade from the candidate list once new measurements arrive. The picture shifts as the data improves. Consider TOI 270d, a planet about twice the size of Earth, circling a small red star roughly 70 light-years away. Some studies have suggested its atmosphere holds water vapor, methane and carbon dioxide, with hints that a deep liquid ocean could lie beneath a thick hydrogen blanket. Other researchers read the same data and see something quite different. They argue the planet may be hot and steamy all the way through, with no real surface at all. Both views come from the same starlight, filtered through the same distant air. The disagreement itself is part of the story. Then there is LHS 1140b, a slightly heavier world, circling a cool, quiet star about 48 light-years from us. Early measurements suggested a rocky planet with a thin atmosphere. Newer measurements have hinted that it could instead be a water-rich world with a soft hydrogen envelope above a deep, dark sea. The change came not from the planet itself, but from our growing ability to listen carefully to the light passing through its sky. Each new look revises the portrait. Each revision opens a new question. A handful of other names drift through the research papers, each with its own uncertainties. Some sit at the warm edge of their star's habitable zone, where a hydrogen sky would press down on water, just barely cool enough to stay liquid. Others orbit further out, where only a thick hydrogen blanket could keep an ocean from freezing solid. Few may turn out to be ordinary mini Neptunes after all, with no real surface, no real sea, only endless gas thinning into endless gas. We simply do not yet know which is which. The catalogue itself is changing in a deeper way. 20 years ago, the idea of a Hycean world barely existed. The very category was proposed only recently, as astronomers tried to make sense of the strange middle ground between rocky planets and small gas giants. Before that, these worlds were lumped together as super-Earths or mini-Neptunes, and nobody thought much about oceans beneath their clouds. The vocabulary had to catch up to the data. Now the vocabulary is shaping how we look. That shift matters. When you have a name for a thing, you start to see it everywhere. Researchers now sift back through old observations, asking whether planets once dismissed as uninteresting might in fact be hidden ocean worlds. Some candidates emerge from that careful rereading. Others quietly fall away. The list grows and shrinks at the same time, like a tide pulling on its own shore. There is also a slower change happening in the planets themselves. Over millions of years, a Hycean Worlds atmosphere may be drifting away into space, one light hydrogen molecule at a time. The hydrogen that makes these skies so thick is also the easiest gas for a planet to lose. Stellar winds pluck at the upper layers. Ultraviolet light breaks apart molecules and sends the fragments wandering off into the dark. A world that is Hycean today may, in some distant future, be something else entirely. A smaller, drier place with a thinner sky, or perhaps a rocky shore left behind beneath an evaporated sea. Or it may hold its atmosphere for ages, depending on the strength of its gravity and the temper of its star. We do not yet know which fate is more common. So when we speak of these worlds, we are speaking of a moving picture. The catalogue is changing. The planets within it are changing. Our understanding of the category is changing. Even our instruments are changing, year by year, returning sharper signals from the same distant systems. The cousins of K2-18b are scattered across the sky and across the catalogue, and many of them have not yet been recognized for what they might be. Some of the most interesting candidates may still be sitting quietly in old data, waiting for a fresh eye and a better model to notice them. For tonight, it is enough to picture them, a soft constellation of possible oceans, none of them confirmed, all of them suggested. Worlds in slow motion, worlds still becoming themselves, and still becoming themselves in our minds. Light is the first question any biologist asks about a strange world. Where light goes, life on Earth tends to follow, or at least it tends to begin there. So when we picture a deep ocean, wrapped under a thick hydrogen sky, we have to ask what the light looks like once it finally reaches the water. And we have to ask, what kind of living thing, if any, could ever make use of it? The light from a Hycean Worlds star would not arrive the way sunlight arrives at Earth. It would have to pass through a hydrogen atmosphere many times deeper and heavier than our own. Hydrogen and helium are nearly transparent to visible light, which is part of what makes these worlds so interesting. But the haze layers above the ocean, thin clouds of methane droplets, ammonia ice crystals, or unknown organic particles, would soften the colors. The sky, seen from the waves, might glow a pale lilac or a dim copper, depending on what floats in the upper air. Below that sky, the ocean would receive a quieter version of starlight. Many Hycean candidates orbit red dwarf stars, which shine more strongly in red and infrared light than our sun does. A red dwarf's glow is warm and dim to human eyes, the color of an old ember. So the surface of a Hycean sea, lit by such a star, might look like a calm pond at sunset that never ends. The water itself would absorb the red wavelengths quickly, within the first tens of meters, leaving the deeper layers in a soft blue gloom that fades to black. This brings us to the great question of whether photosynthesis could work down there. On Earth, plants and algae use visible light to split water and build sugars. They work best in the blue and red bands. A Hycean ocean lit by a red dwarf would be rich in exactly the wavelengths some Earth life loves most. One theory, gently proposed by a number of astrobiologists, is that simple photosynthetic life could thrive in the upper few meters of such a sea, drifting like green dust just below the waves. A competing view is more cautious. The thick hydrogen atmosphere might scatter and dim the light enough that only a thin band near the surface would receive enough energy for photosynthesis. And the chemistry of a hydrogen-rich ocean might not favor the same reactions that work on Earth. Life there, if it exists, might draw its energy from something else entirely, from dissolved hydrogen reacting with carbon dioxide, a process some Earth microbes already use in deep dark places. In that case, light would be a luxury, not a requirement. There is also the question of whether the ocean has a bottom that life could cling to on Earth. Hydrothermal vents on the seafloor host entire ecosystems that never see the sun. Their inhabitants feed on chemicals seeping from cracks in the rock. A Hycean world might have no rock floor at all, only a deep transition into exotic, high-pressure forms of ice or slushy mixtures we have never sampled. Whether vents can exist in such a place, and whether anything could live around them, remains an open question. Even if photosynthesis works, the creatures using it would not look like anything from a familiar textbook. Without land, there would be no roots, no shores, no tide pools. Life might float in suspended sheets, slow swarms of cells holding gas bubbles for buoyancy, drifting with the currents under a copper sky. Or it might gather in long ribbons trailing through the upper waters, catching the dim red glow with pigments tuned to wavelengths no Earth plant uses. These are guesses, and they are meant to be. The honest answer is that we do not know what shapes life would take in such a place, or whether life would arise there at all. Some researchers wonder if a Hycean ocean might be too still for biology to take hold. A thick atmosphere damps wind, and a tidally locked world might lack strong day-night mixing. Without churn, nutrients could settle out of reach. Others argue the opposite, that gentle, steady conditions are exactly what early life needs to take root. The way a quiet pond on Earth often holds more life than a stormy coast. So the light tells us very little for certain. It tells us that a sky exists, that some warmth reaches the waves, that the upper ocean is not entirely dark. Beyond that, it leaves room for almost any answer. Whether anything stirs in that dim blue water, turning its face toward a red sun it has never seen, is a question we cannot yet ask the water itself. Sunlight is the quiet question at the heart of every Hycean world. On Earth, sunlight does more than warm the ground. It feeds the plants, which feed almost everything else. It drives the wind. It paints the sky. The question of whether life could grow on an ocean world wrapped in hydrogen comes down, in part, to whether enough light can reach the water below. A thick hydrogen atmosphere is not the same as the thin air above our heads. Hydrogen molecules scatter blue light strongly, much as our own atmosphere does. But the column is far deeper. A Hycean sky might be tens or even hundreds of kilometers thick before reaching the sea. Light, entering at the top, has a long way to fall. Some of it bounces back into space. Some of it warms the gas itself. Only a fraction makes it down to the waves. The color of that surviving light is one of the open questions. If hydrogen scatters the blues away, what reaches the ocean might lean towards soft reds and dim golds, like a perpetual late afternoon. If clouds form high up, hazes of methane or droplets of water, or fine particles we have not yet named, the light below might be dimmer still, a grey and silver glow with no clear sun overhead. We do not know which picture is closer to the truth, because we have never stood beneath such a sky. Some researchers wonder whether photosynthesis, the trick that lets Earth's plants turn light into food, could work under these conditions. On Earth, certain microbes already live in very dim places, deep in lakes, under ice, near hot vents, and use faint red light to grow. If a Hycean ocean held even a thin sunlit layer near the top, perhaps similar life could float there, drifting in the slow currents. Other researchers are less hopeful. They point out that hydrogen, in great quantity, may simply rob the water of the kind of chemistry photosynthesis needs. The answer is not yet in. There is another way light might matter on such a world. Stars are not silent in the way we imagine. They hum and shudder with internal motions. Sound itself cannot cross the vacuum between stars and planets, but the light a star sends out carries the fingerprints of those vibrations. When scientists translate those small flickers into audio, the result is a low, rolling tone, almost like a distant bell struck underwater. A red dwarf, the kind of small, cool star many Hycean candidates orbit, would have its own quiet song, slower and deeper than our sun's. If you stood on the surface of a Hycean ocean, you would never hear that stellar hum. You would hear the sea instead. The thick atmosphere, much denser than ours, would carry sound in unusual ways. Waves crashing under such heavy air might sound muffled and close, the way voices sound inside a small room with soft walls. Thunder, if storms formed there, might roll on for a long time before fading, the dense gas slow to let go of each pulse. Some theorists Imagine a constant, gentle hiss, the wind sliding endlessly over water that has no shore to break against. We cannot record any of this, of course. The nearest Hycean candidate is more than 100 light-years away. What we can do is listen, in a different sense, to the light such planets send us. When a Hycean world passes in front of its star, a thin sliver of starlight filters through its upper atmosphere on the way to our telescopes. That light arrives carrying chemical signatures. Some scientists describe the process of reading those signatures as listening, a slow, patient act of separating one faint note from a great wash of noise. The trouble with sunlight, then, is also the gift of sunlight. The same beams that might or might not feed life down in the sea are the only messengers we have. Everything we suspect about Hycean worlds, the depth of their oceans, the height of their clouds, the chemistry of their air, has been pieced together from a few photons that brushed through a planet's edge before continuing across the void. It is a quiet kind of knowledge, gathered grain by grain, and it leaves more questions than answers. Whether enough light truly reaches those distant seas to wake any kind of biology is still unknown. Whether the songs of those oceans, if such songs exist, would resemble anything Earth has ever heard, is also unknown. For now, we sit with the silence between us and listen to the faint flicker of starlight and wonder what is happening beneath that far, slow, hydrogen sky. Water is a simple molecule, 2 atoms of hydrogen, 1 of oxygen, bonded in a quiet little bend. Yet for something so small, it follows a surprisingly rich set of rules. As you change its temperature and the pressure pushing down on it, water rearranges itself into different forms. On Earth, we know 3 of these forms well: ice, liquid, and vapor. On a Hycean world, the mathematics of water becomes far stranger and far more beautiful. Scientists draw the behavior of water on a kind of map called a phase diagram. The map has 2 axes, one for temperature, one for pressure. Every point on the map tells you what shape water will take at those conditions. Near the bottom left, where it is cold and the pressure is light, water freezes into ordinary ice. In the middle, where Earth lives, water flows as a liquid. Push the temperature up, and it drifts away as steam. The rules are clean, and they hold across the universe. But the map does not stop where Earth stops. Push the pressure higher, and new shapes of ice begin to appear. Not the gentle ice you scrape from a windshield, but dense, crystalline forms that only exist when something heavy is pressing down. Researchers have given these forms simple names, like Ice 6, Ice 7, and Ice 10. Each is a different way the water molecules can lock together when squeezed. Each appears at a precise spot on the phase map, predicted by equations that fit on a single page. On a Hycean world, this matters in a quiet and elegant way. The ocean is deep, perhaps hundreds of kilometers from top to bottom. At the surface, the water is liquid, kept warm by the hydrogen blanket above. As you sink, the pressure rises with depth, following a smooth and predictable curve. For every kilometer you descend, the weight of the water above grows. At some point, the equations say, the pressure becomes high enough that ordinary liquid water can no longer exist. The molecules begin to pack into one of those exotic ice forms instead. This may be the floor of a Hycean sea, not rock, but ice, a vast, smooth layer of high-pressure ice, sitting beneath the warm ocean, separating the water from any rocky core deeper still. Some models place this floor a few hundred kilometers down. Other models place it much deeper, or suggest it may not form at all if the world is small enough and the ocean stays shallow. The math gives a range of answers, and the answer depends on numbers we do not yet know. There is also the question of what happens near the top, where the ocean meets the hydrogen sky. The temperature might climb close to the boiling point of water at that pressure. The phase map tells us that under a thick atmosphere, water can stay liquid at temperatures well above 100 degrees Celsius. On Earth, water boils at 100 because the air above is thin. Press down harder and the boiling point rises. Some Hycean models suggest surface waters warm enough to brew tea, yet still calm and liquid because the hydrogen above holds them in place. One theory says these warm upper layers might mix freely with cooler waters below, stirred by gentle currents. Another theory says the warm layer floats on top in a stable cap, sealed off from the deeper, cooler ocean. The mathematics of fluid layers, of density and salt and temperature, allows for either picture. Which one is real depends on details we cannot measure from light years away. There is a quiet elegance in all of this. The same equations that describe a glass of water on a kitchen table also describe an ocean half a galaxy away. The phases of water, the curves of pressure and heat, the smooth lines on a phase diagram, they do not change. A water molecule on K2-18b obeys the same rules as one in a raindrop, falling outside your window. The universe is consistent in this way, and there is something soothing in the thought. What remains unknown is which points on the map a given Hycean world actually occupies. We can sketch the possibilities, we can run the numbers and draw the lines. We cannot yet stand on the shore and measure the temperature with our hands. The math gives us a frame. The frame holds many possible pictures, and we do not know which one nature has painted. So the ocean of a Hycean world may have an icy floor, or it may not. It may have a boiling skin, or a layered calm, or a steady warm mixing from top to bottom. The equations allow each version. They wait, patient and unchanged, for the measurements that will tell us which is real. Picture a Hycean world from far away, a pale blue marble wrapped in a soft haze of hydrogen. From this distance it looks calm, almost still, but every ocean has tides, and a Hycean ocean would be no different. The pull of the parent star, the tug of any moons, the slow rotation of the world itself, all of these would lift and lower the water in long, patient swells. Tides on Earth are gentle things. The moon raises the seas by a meter or two, and the sun adds a smaller pull. We have grown up with this rhythm and barely notice it. On a Hycean world, the rhythm could be very different. Many of these planets likely orbit close to small, cool stars called red dwarfs. Stars that burn slowly and live for trillions of years. Close orbits mean stronger tidal forces. The star would pull the ocean into a long, slow bulge that travels around the planet as it spins. If the world is tidally locked, meaning one side always faces the star, the tidal bulge would not travel at all. It would sit fixed beneath the star, a permanent swell of water held in place by gravity. The night side would have its own steady low, a quiet basin of deeper sea. The question of whether such a frozen tide could still support a stable climate is one researchers are only beginning to explore. Some models suggest the thick hydrogen atmosphere would carry heat efficiently from the day side to the night side, smoothing out the temperature. Other models suggest the night side could grow cold enough to freeze, locking water away as ice and slowly draining the ocean. This is part of the fragile balance. A Hycean world depends on its hydrogen blanket to stay warm enough for liquid water, far from its star. If the atmosphere were thinner, the surface would freeze. If it were thicker, the pressure and heat at the bottom of the ocean would climb past the point where life as we understand it could survive. The window of conditions that allows a deep liquid sea beneath a hydrogen sky may be narrow. How narrow exactly remains an open question. Consider how delicate Earth's own balance is. Our atmosphere is thin, a fragile shell about 100 kilometers deep on a planet more than 12,000 kilometers across. Move our world a little closer to the sun, and the oceans begin to boil away. Move it a little farther, and they freeze solid. The tilt of our axis gives us seasons. The moon stabilizes that tilt over millions of years. Plate tectonics recycles carbon and keeps the greenhouse effect in check. Each piece supports the others, and the whole system has held together for billions of years. A Hycean world would have its own set of balancing acts, and we do not yet know which ones matter most. The hydrogen atmosphere has to stay put despite the constant pressure of stellar radiation trying to strip it away. The ocean has to remain liquid from top to bottom, even though pressure at the floor could be thousands of times Earth's surface pressure. The chemistry of the sea has to stay within ranges that allow molecules to form and react. Change any one of these too much, and the world might tip into something else entirely. A steam-shrouded greenhouse, a frozen mini Neptune, a barren rock stripped of its skies. Some researchers wonder whether tidal heating itself could become a problem. A close orbit around a red dwarf flexes the planet's interior, generating warmth from friction deep inside. A little of this heat might be helpful, keeping the ocean from freezing at its base. Too much, and the seafloor could grow restless, churning the chemistry of the water in ways that may or may not favor stable conditions. The right amount is unknown. The line between helpful warmth and harmful turmoil has not been mapped. There is something quietly moving about. How many things have to go right for a world to hold an ocean for a long time? On Earth, the conditions came together by a sequence of accidents we are still piecing together. On a Hycean world, we do not even know the full list of conditions. We are guessing at the variables, sketching the rules, watching distant points of light for hints. The balance, if it exists, may be even more delicate than our own, or it may be more forgiving in ways we cannot yet imagine. For tonight, picture that pale blue marble again, its hydrogen sky pressing softly on a global sea. Somewhere beneath the haze, a slow tide rises and falls, holding to a rhythm we may never directly see. A hydrogen atmosphere is a fragile thing, even when it weighs down on an ocean 100 kilometers deep. Hydrogen is the lightest gas in the universe, and lightness is a kind of restlessness. The faster a gas molecule moves, the easier it slips away from a planet's grip. Hydrogen, being so light, moves the fastest of all, and so, on every world wrapped in hydrogen, a quiet drift is always happening at the top of the sky. Atom by atom, the atmosphere is leaking into space. This slow escape is one of the deepest open questions in the study of these ocean worlds. We do not yet know how long a thick hydrogen blanket can last, around a planet only a few times more massive than Earth. We do not know how much depends on the star, how much depends on the planet's own warmth, and how much depends on quiet processes hidden inside. The simplest picture goes something like this. High above the ocean, where the air thins to almost nothing, ultraviolet light from the star strikes hydrogen molecules and breaks them apart. The freed atoms, heated and excited, rise even higher. Some reach speeds that gravity can no longer hold. They drift outward, one by one, into the dark. Over billions of years, those single atoms add up. But the rate of that leak is fiercely debated. One school of thought suggests that ocean worlds around calm, older red dwarf stars could hold onto their hydrogen for many billions of years. The star's gentle output would mean a gentle erosion, slow enough that a planet born with a thick shroud might still wear it long after life had time to begin. Under this picture, Hycean Worlds would be patient, durable, and common. Another school sees things differently. Red dwarf stars, especially when young, throw out fierce bursts of ultraviolet and X-ray light. Some researchers wonder whether those early storms strip away most of a planet's hydrogen in the first few 100 million years. If that is true, then many candidate ocean worlds we see today might be the lucky survivors, the ones that began with so much hydrogen that even a brutal youth could not finish them off. Others, less fortunate, would have shed their skies long ago and now sit as bare rocky cores, no longer Hycean at all. The radius gap in the exoplanet catalogue hints that this stripping really does happen. Planets cluster into two groups, one a little larger than Earth and one a little larger still, with fewer worlds in between. The space between them may be a graveyard, full of planets that lost their atmospheres and shrank. But whether a true Hycean world sits safely above that gap or slowly slides into it remains unclear. There is also the question of what the ocean itself contributes. Water can split into hydrogen and oxygen under the right conditions, and some of that fresh hydrogen might rise into the air, slowly topping up what escapes above. Whether such refilling is fast enough to matter, no one knows. The chemistry between sea and sky on these worlds is a story we have not yet learned to read. Internal heat plays a role as well. A warm core can puff the atmosphere outward, making the upper layers easier to lose. A cooler core lets the air settle, holding it close. We cannot yet measure the inner warmth of a planet light years away, so this remains a hidden variable in every model. What makes the slow escape so fascinating is that it ties the lifespan of a Hycean ocean to forces operating across vastly different scales. The wind of a star, the chemistry of a single molecule, the slow heartbeat of a planet's interior, all of them meet at that thin upper edge of the sky where hydrogen quietly drifts away. Change any one of them and the whole world's future shifts. And so we are left wondering, are the ocean worlds we suspect we have found young and short-lived, soon to lose their warm blankets and freeze into something else entirely? Or are they ancient and stable, carrying their hydrogen seas across timescales long enough for strange chemistries to ripen into something we might one day call alive? The same observations support both pictures, depending on which assumptions you trust. For now, the slow escape of hydrogen is one of those gentle puzzles that may take a generation to solve. Each new telescope adds another small clue. Each refined model nudges the estimates one way or the other. The leak goes on, somewhere out there in the dark, atom by patient atom, and we do not yet know whether we are looking at worlds at the beginning of their stories or somewhere near the end. Even the finest telescopes we have today can only tell us so much about these distant ocean worlds. We catch a thin sliver of starlight as it brushes past a planet's atmosphere. We read the fingerprints of a few molecules. We guess at the temperature, the size, the gravity. Beyond that, almost everything remains hidden. The surface, if there is one, stays invisible. The clouds blur into averages. The ocean below, if it exists, is only a guess, shaped by chemistry and math. The James Webb Space Telescope, floating quietly 1 million miles from Earth, has already shown us hints of carbon dioxide and methane in the air of one possible Hycean world. Those signals are faint and disputed. They sit at the edge of what the instrument can measure. Some researchers see a clear story in the data. Others see noise that has been read too generously. The truth waits behind more observations more starlight, more patient hours of staring. Future telescopes may push the view a little deeper. There are designs being studied for missions that could directly image small planets around nearby stars, blocking the glare of the parent star with delicate shades or shaped mirrors. If such a mission flies, it might let us see a Hycean world as more than a shadow crossing its sun. We might catch the faint glow of its atmosphere, the color of its clouds, perhaps even the shimmer of an ocean reflecting starlight. But none of these instruments exist yet. The plans are sketches. The launches, if they happen, are decades away. Imagine the slow march of time beyond that. 1,000,000 years from now, the constellations we know will have drifted into new shapes. The stars that host today's candidate Hycean worlds will still be burning, most of them, since red dwarfs live for trillions of years. Those slow, cool stars are patient hosts. Their planets may keep their hydrogen blankets for ages longer than Earth has existed. If life is brewing beneath those skies, it has time, vast, almost unimaginable time. In 1,000,000,000 years, our own sun will grow brighter and hotter, slowly boiling Earth's oceans into the sky. Our planet will become something stranger, drier, more hostile. But the Hycean worlds around red dwarfs will hardly notice that 1,000,000,000 years pass. Their stars will still be young by their own measure. Their oceans, if the hydrogen atmosphere holds, may still slosh gently against pressure layers deep below. The mystery we wonder about tonight may still be a mystery then, only studied by different eyes in different ways, by minds we cannot picture. The universe keeps making new things, while old things fade. New stars form in dusty clouds. New planets gather from disks of debris. Somewhere in the galaxy right now, a Hycean world is being born. Its first storms gathering in a sky that has never seen a sunrise. Somewhere else, an older Hycean world is losing the last of its hydrogen. The ocean below cooling into something more familiar. We are looking at a population of worlds at every stage of their lives, all at once, scattered through the catalogue, like leaves at different points of falling. What our telescopes cannot see today, they may see in 50 years. What they cannot see in 50 years, perhaps another generation will glimpse, or perhaps the answer will come from a direction no one expects. A new technique, a new kind of detector, a quiet idea from a researcher who has not yet been born. Discovery rarely follows a straight line. It wanders. One possibility is that future studies will confirm Hycean worlds as a real and common class, with their own chemistry, their own weather, their own patient oceans. Another possibility is that the category will dissolve as we learn more, and we will find that most of these candidates are something else entirely, something we have not yet imagined. Both outcomes would be interesting. Both would teach us. Neither would close the question, only reshape it. For now we sit with the limits of our instruments. We sit with the soft hum of a telescope 1,000,000 miles away, gathering photons, one at a time. We sit with the knowledge that the galaxy is far larger than our ability to study it, and that most of its worlds will live their entire lives without ever being seen clearly by anyone. The unseen is not empty. It is simply waiting beneath those thick hydrogen skies. In oceans we may never touch, something might be drifting, or settling, or stirring. The future of this question belongs to telescopes that have not yet been built, and to minds that have not yet begun to wonder. Step back now. Let the picture grow wider than a single planet, wider than a single star. The question of Hycean worlds is really a question about the whole quiet sky above you. How common is water in the universe? How common is warmth? How common is the slow chemistry that lets a world become something more than rock and gas? These questions ripple outward from one strange ocean to every corner of the galaxy. Think of where the water came from in the first place. The hydrogen in any Hycean sea is older than the Earth, older than the Sun. It formed in the first few minutes after the universe began, when everything was hot and dense and bright. That hydrogen drifted for billions of years before gathering into clouds, before collapsing into stars, before swirling into the disks where planets are born. The oxygen, mixed with it, came later, forged inside earlier generations of stars that lived and died before our solar system existed. Every drop of water on every world is a meeting between the oldest atoms and slightly younger ones. It is a quiet handshake across deep time. The atoms in your own body share this history. The hydrogen in the water you drank today is nearly as old as the universe itself. The calcium in your bones, the iron in your blood, the carbon in every cell, all of it was cooked inside ancient stars and scattered when those stars died. You are walking around with pieces of the same elemental kitchen that makes Hycean oceans possible. The difference between you and a sea on a faraway world is mostly a matter of arrangement. Same ingredients, different recipe. This is why the disagreements among researchers feel less like arguments and more like the slow, careful work of figuring out a family tree. Some scientists believe Hycean worlds may be common, scattered through the galaxy like quiet blue marbles wrapped in haze. Others suspect the category itself may turn out to be smaller than hoped, with many candidates revealing themselves as something else entirely. Perhaps molten interiors under thick steam, perhaps mini Neptunes with no real ocean at all. Both views rest on the same evidence. They simply read it differently. The same is true for the question of life. One camp wonders whether a deep hydrogen-blanketed ocean could host the simple chemistry that on Earth eventually gave rise to everything. Another camp doubts that photosynthesis or any familiar metabolism could work under such heavy skies, where light is filtered, pressure is enormous, and the chemistry of dissolved gases is unlike anything in our seas. Neither side can settle the matter yet. The instruments are still too young. The data is still too thin. What is striking is how the disagreement itself is a kind of progress. A generation ago, no one argued about Hycean worlds because no one knew they might exist. The very fact that careful people now sit on opposite sides of a careful debate means the universe has handed us something new to think about. Each new measurement, each contested signal, each strange spectrum from a distant transit adds another small piece to a puzzle no one alive may finish assembling, and the puzzle is enormous. There are more stars in the observable universe than grains of sand on every beach on Earth. Most of those stars host planets. Many of those planets fall into the size range where Hycean conditions might be possible, even if only a tiny fraction of them truly hide deep oceans under hydrogen skies. The total number could still be staggering. Worlds and worlds and worlds, each with its own weather, its own currents, its own slow rhythms beneath a sky we will never personally see. The connection runs both ways. Studying these distant oceans tells us something about our own. Our planet is rare in some ways. A thin atmosphere, a single moon, a surface where rock and water meet in long, uneven coastlines. But Earth is not separate from the cosmos. It is one solution among many to the same ancient problem of how to hold water on a warm world long enough for interesting things to happen. Hycean planets, if they exist as imagined, would be a different solution to the same problem. So when researchers disagree about K2-18b, about dimethyl sulfide, about the depth of an ocean we cannot see, They are really disagreeing about how many ways the universe knows how to make a home. The answer is still open. It may stay open for a long time. The atoms that wonder about it are the same atoms that built the worlds in question. That by itself is a quiet kind of marvel to carry with you toward sleep. Let your thoughts drift one last time out past the comfort of our own sky. Picture a world we have never named with any certainty. A planet circling a small red star many light years from here, turning slowly in the dark. There is no shoreline on this world. There is no harbor, no continent, no patch of dry earth anywhere on its surface. From pole to pole, it is ocean, and above the ocean, a sky of hydrogen, thick and soft, glowing faintly in the long red light of its sun. We do not know for certain that this world exists. We have hints, we have candidates, we have measurements that disagree, and chemistry that puzzles us. The signals are faint, the instruments are clever, but the distances are cruel. What we have, more than anything, is a question quiet enough to carry you into sleep. Imagine looking down on such a planet from far above. The clouds would be pale, perhaps tinged with the rust of dissolved iron or the gold of organic haze. Beneath them, an ocean deep enough to drown every mountain Earth has ever raised. The water would not be still. Slow waves would roll across it, pushed by winds heavier than any breeze we have ever felt. Yet, from a great distance, the whole world would look serene. A single blue marble, smooth and unbroken, drifting through the long night. We do not know what lives there, if anything lives there at all. Some researchers wonder whether the warm, alkaline depths could cradle simple cells. Others suspect the pressure and chemistry would be too unkind, the sunlight too dim, the hydrogen sky too heavy. Both views remain open. Both views remain beautiful in their own way. A living ocean would be wonderful. A sterile ocean would still be a marvel. An entire world of water turning patiently in the dark, waiting for nothing, needing nothing. Picture the night side of such a planet. The red sun has slipped below the horizon, and the hydrogen sky has darkened to a deep wine color. The ocean glows faintly, lit from within by whatever moonlight bends through the thick air. The waves move slowly, as if they too are tired, and if there are creatures down in the depths, they move slowly as well, breathing dissolved gases we can barely imagine, drifting in currents that have been turning since the planet was young. There may be billions of such worlds. There may be only a handful. The radius gap in our catalogues hints at many. The harsh light of young stars hints at fewer. We cannot yet tell which story is true. For tonight, both stories can sit beside each other like two candles in a quiet room. Closer to home, our own planet turns. Your room is dark. Your breath has slowed. The Earth carries you gently around our sun, and the sun carries the Earth gently around the center of the galaxy, and the galaxy carries us all through a darkness too large to feel. None of it asks anything of you. None of it needs you to solve it tonight. Somewhere, light is leaving a hydrogen sky right now. It will travel for 100 years, or 1,000, or 10,000. Long after this night is over, that light will still be moving toward us, carrying its small story. Maybe a future instrument will read it. Maybe a future listener will hear about it on a quiet evening like this one, and wonder, as you are wondering now, whether anything was alive beneath those clouds. The mystery will outlast us. That is part of its kindness. We do not have to finish it. We only have to hold it for a little while, the way you might hold a smooth stone in your palm before setting it back down. So set the question down now. Let the hydrogen sea keep turning without you. Let the red star keep shining without anyone watching. Let the waves roll on under a sky that has never known a human footprint and may never need to. The universe is vast. The universe is gentle in its own slow way, and you are held, small and safe, on a blue world of your own, while 100 billion other worlds drift on through the dark. We may learn more about Hycean oceans in the years ahead. We may not. Either way, the wandering itself is enough. Tonight, that is all we needed. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.